This video presents solutions for the thermocouple problems number 10 through 17 on page 30 of the thermometry unit. Thermocouple problem number 10. We have a cold junction or meter temperature of minus 14 Celsius with a type J thermocouple producing a millivolt reading of plus 4.8 millivolts, which tells us that the measuring junction is hotter than the meter. Calculate the temperature of the hot junction, which is the measuring junction. We want a type J table for degrees Celsius, and that would be here. So I've written the problem out again. The first thing I would do is draw a diagram to illustrate the situation we have. So we have the meter at minus 14 degrees Celsius. That's the reference junction. We'll have the measuring junction. So what temperature is that? Freezing point is somewhere between the measuring junction and the reference junction. We'll find that out when we do the problem. This is the reference temperature, 0 degrees Celsius. Alright, so if our meter was at 0, then we could simply read the table and find what temperature corresponds to 4.82 millivolts. But it's not at 0. Well, why don't we look up the reading between 0 and minus 14, and we'll subtract that from the 4.82, and that'll give us the distance in millivolts from here to the measuring junction. Right? So let's look on the table at minus 14. So minus 14 degrees Celsius is minus 10, 11, 12, 13, 14. Minus 14 is minus 0.699 millivolts. So the table is telling us that if we had our meter reference junction at 0 and the measuring junction was at minus 14, that would read minus 0.699 millivolts. Now, the signs can be confusing, so it's helpful to think in terms of magnitude. The magnitude of the millivolt reading corresponds to delta T. It's about 0.7 millivolts. This is 4.82 millivolts. If our meter was situated like this, what would we read? We'd read 4.82 minus 0.699. We'd read 4.121 millivolts. We'd read less millivolts because it'd be a smaller delta T. So let's look up on our table and find out what temperature corresponds to 4.121 millivolts. So 4.121. Here's 4.079 at 78 and 4.133 at 79. Okay, let's write those on our diagram. 4.079 at 78. This is 4.121 millivolts at some temperature at 78 degrees Celsius. We read 4.079 millivolts, and the next highest temperature, 79 degrees C, 4.133 millivolts. So between 4.133 and 4.079, this is 0.054 millivolts. And then between 4.121 and 4.079, that is 0.042 millivolts. So this represents about 0.8 of the total distance. So we can say that 1 Celsius degree equals 0.054 millivolts. That's our conversion factor. 0.042 millivolts times 1 Celsius degree per 0.054 millivolts. That's about 0.8 Celsius degrees, so we're going to add that 0.8 to 78, and this therefore is 78.8 degrees Celsius. So the problem said that with the meter at minus 14, it read 4.82 millivolts. Calculate the hot junction temperature. Well, we'd said the millivolt reading would be less if in fact the meter was at 0 instead of minus 14. How much less? So we looked in the table and saw that for a temperature difference between 0 and minus 14, that was minus 0.7 millivolts. We took the magnitude of that 0.7, subtracted it from 4.82 and got 4.121. That would be the reading we would get if the meter was at 0. And then we narrowed that down and said, well, that's between 78 and 79 Celsius, and we interpolated till we found 78.8 degrees Celsius. All right, let's do problem number 11. Number 11 says that the EMF of an iron constant thermocouple, that's type J, was found to be plus 44.4 millivolts. That's pretty high. With a cold junction temperature, that's the meter, at 0 degrees C, right where we want it. If the meter changes to 100, what would be the EMF produced by the thermocouple? That sounds pretty straightforward. Well, let's draw a picture for this. So the meter is at 0 degrees C. That's our reference temperature, and it's also a reference junction, which is kind of neat. And it's reading 44.40 millivolts. And we're not really asked to calculate the temperature, are we? We're not really asked that, so we'll leave it as a question mark. It says, if the cold junction temperature changed to 100, what would it read? So let's, well, that would be shorter then, wouldn't it? 44.4 sounds pretty big. So let's say from 0 to 100, let's look that up in the table. We'll subtract that value from 44.4 and find out the reading from 100 degrees Celsius to our measuring temperature. So 100 degrees C, 5.269 millivolts. We'll subtract that. 5.269 millivolts. If we subtract that from 44.40 minus 5.269 millivolts, we will get a value of 39.13 millivolts. And that's it. We weren't really asked to calculate the measuring junction temperature. Right, so let's take a look at question number 12. We have an iron constant thermocouple. It's placed in a known temperature of 400 Fahrenheit. And if the thermocouple reads 10.81 millivolts, what's the temperature of the meter? That's kind of a switch. So the measuring junction is at 400 degrees Fahrenheit. We're asked to calculate this temperature, which is the meter or the reference junction. It measures 10.81 millivolts. Well, what we can do is figure out from the table how many millivolts would be generated from the freezing point to 400 Fahrenheit. Degrees Fahrenheit table, 400 degrees Fahrenheit, 11.025 millivolts for a type J thermocouple. 11.025. So that's bigger than 10.81. So what that's saying is if we had our meter at the freezing point, we'd read 11.021 millivolts. So this is 32 degrees Fahrenheit. That's the freezing point. What we could do is figure out the distance between here and here, right? This would be 11.021 subtract 10.81 millivolts. That's equal to 0.215 millivolts. And this is the position where our meter is situated. That's its temperature, right? That's what we're asked to calculate. So let's look on the table and find out what 0.215 millivolts corresponds to as a temperature. 39 is 0.196 and 40 is 0.225. So it lies in between 39 and 40. Let's write those down, 196 and 225. So I'm going to exaggerate a little bit. At 39 degrees Fahrenheit, we have 0.196 millivolts. At 40 degrees Fahrenheit, we have 0.225 millivolts. And we are at 0.215 millivolts, somewhere in between 39 and 40. What temperature does that correspond to? Well, it's 39 point something. Let's say between 39 and 40. This would be 25 plus 4, that's 0.029 millivolts. And then between 39 and our temperature, that's 15 and 4, that's 0.019 millivolts. So this is a conversion factor, that's 1 Fahrenheit degree, so I can say 0.019 millivolts times 1 Fahrenheit degree per 0.029 millivolts. That's about 2/3, pretty close. That's 0.67 or 0.7. So that would tell me that my temperature here will be 39.7, because it's 0.7 Fahrenheit degrees greater than 39. Does that make sense? So we have a thermocouple placed in a temperature of 400 Fahrenheit, and it reads 10.81 millivolts. What's the temperature? Don't know, but we could look up 400 in the tables and find that between the freezing point and 400, it reads 11.021 millivolts. So 10.8 isn't as wide as 11.02, so it must be a smaller temperature span. So I draw it as so, and then what I can do is calculate the millivolt reading from the freezing point to what we're given here. The difference between 11.02 and 10.8 is 0.215, and now I can look up on the tables what temperature corresponds to 0.215 millivolts. Yeah, okay. So let's try problem number 13. We're told that at a temperature of 447 Celsius, a type J thermocouple produces an EMF of 8.11 millivolts. Calculate the temperature of the cold junction, that would be the meter, and therefore this must be the temperature of the other junction, which is the measuring junction. Right? So let's draw something for that. Now, it's kind of like the last one, it's kind of mixed up. We want to calculate the temperature of the meter. We're told that the temperature is at 447. All right, let's look on the table and find the millivolts that correspond to a temperature difference from the freezing point to 447. 440.9, 0.8, 0.7. That's 24.444 millivolts from freezing point to 447. 24.444 millivolts. Now that would be from the freezing point, which is 0 degrees C, up to 447 degrees C. Now what about our thermocouple? Our couple is at 447, but its meter is closer to it. It's only 8.11 millivolts difference. Let me draw something like this. All right. So we're measuring 8.11 millivolts from our meter temperature, which is the reference junction, to 447, which is the measuring junction. The question is, what is the temperature of the meter? What's this temperature? Well, why don't we subtract 8.11 from 24.4, and we'll figure out what reading we'd get if we had a thermocouple set up like this. So this is 24.444, subtract 8.11, and that would be 16.334 millivolts is the EMF generated if we had a thermocouple with the meter situated at the freezing point and its measuring junction was at the reference junction. Right. So let's look that up. 16.334 millivolts. It's right here. 16.327 is 300. 16.344 falls within that range. So 16.327 and 16.383. 300 degrees C. It was 16.327 millivolts. At 301 degrees C, 16.383 millivolts, and we're reading 16.334 millivolts. How many degrees C? Well, 334 is a lot closer to 327 than it is to 383, but let's work it out. So this distance, 1 Celsius degree, that is a span of 0.056 millivolts. I think that's correct. And then between 300 and our temperature, this is only 0.007 millivolts. So that's 1/8, if that, which is 0.1, but in any case 0.007 millivolts times, this is 1 Celsius degree, 1 Celsius degree per 0.56 millivolts. So this works out to be, again, it's 1/8 or 0.1 Celsius degrees, greater than 300, and therefore this will be 300.1 degrees Celsius. Looks good. So let's quickly recap that. So we're told it's 447 Celsius and it's producing 8.11 millivolts. What is the temperature of the meter? We can look up the millivolt range that would be produced from 0 to 447, 24.444. Let's subtract 8.11 from that. Here's a span of 16.334 from the freezing point. We look it up on the table. We find out that the nearest points are 300 and 301, and we interpolate to find the exact value. Looks good. So problem 14 says the EMF of an iron constant thermocouple was 5.9 millivolts when the meter is at 83 Fahrenheit. Calculate the temperature of the hot junction. In other words, calculate the measuring junction temperature. So this is 5.90 millivolts. The cold junction temperature is 83. Calculate the hot junction temperature. Well, if the meter was at 32 at the freezing point, then we could look up this value in the table and read the Fahrenheit temperature, but it's not at the freezing point. So let's figure out what the reading would be from the freezing point. Let's take it from 32 degrees Fahrenheit to 83, that distance. We'll add that to the reading from 83 to our temperature, and that should give us the total EMF. So from 32 to 83 degrees Fahrenheit. 83, that's 81, 82, 83 is 1.450 millivolts. This is 1.450 millivolts. and we'll add it to the 5.90 as if we had our thermocouple set up like this. 1.45 plus 5.90 is 7.35 millivolts. So yeah, if we had our meter at the freezing point, we'd read 7.35 millivolts. What temperature is that? Let's read the table. 7.35. At 280, it's 7.336. At 281, it's 7.367. At 280 degrees Fahrenheit, 7.336 millivolts. At 281 degrees Fahrenheit, 7.367 millivolts. Our reading is 7.350 millivolts. What's the temperature in degrees Fahrenheit? All right, so 1 Fahrenheit degree temperature difference in this area corresponds to a millivolt difference of, from 67 to 36, that looks like 0.031 millivolts. And then from 280 to our 0.014 millivolts, which looks like about a half, right? 0.014 millivolts times 1 Fahrenheit degree per 0.30 millivolts. It's going to be 0.5, which tells us our temperature will be 280 plus 0.5, which is 280.5 degrees Fahrenheit. Does that make sense? Right, so from 83 Fahrenheit for the meter to the measuring junction at some temperature, we read 5.90 millivolts. What's that temperature? Let's figure out what the millivolt reading would be if the meter was at 32. So let's add the millivolt reading corresponding to a temperature change of 32 to 83. Gives us 7.35 millivolts. We read the tables and find it's between 280 and 281, and then we interpolate from there. Now part B here says if the temperature of the cold junction changes to 67 Fahrenheit, if it moved down here, what would be the EMF produced? Well, it'd probably be more than 5.9 if it's at 67, but how much more? How can we figure that out? Well, I think what we could do is look up the millivolt reading corresponding to a temperature difference from 32 to 67. Let's say it's somewhere here. We'll subtract it from this total reading of 7.35, and that should give us the difference. So if I'm going to have it at 32 up to 67, let's look that up on the table. 987. That's 0.991, so we just have to subtract that. This is 0.991 from 32 Fahrenheit to 67. If we subtract that from 7.35 of this situation, 7.35 minus 0.991 works out to be 6.36 millivolts. Does that make sense? Well, it's going to be more than 5.9 because we get a bigger temperature spread. We figure out the millivolt reading from the freezing point to 67. That would subtract that from 32 from the freezing point to 280, and that difference would be the millivolts for that. Makes sense. So problem number 15, the measuring junction of an iron Constantan thermocouple is placed in a mixture of ice water and salt that is known to have a temperature of 20 degrees Fahrenheit. That's cold. Remember that 32 Fahrenheit is the freezing point in the Fahrenheit scale. This is below freezing. If the room temperature is 75, calculate the EMF that would be produced by the thermocouple. So here we're asked to calculate the EMF rather than a temperature. Well, given both temperatures, we're told that room temperature is 75. That's where the meter is. and the temperature in the ice salt water bath is 20 degrees Fahrenheit. Calculate the EMF, or millivolts. Notice I've drawn this backwards. I've drawn it from right to left because I just like to show for cold temperatures I'll put the measuring junction on the left rather than the right. How are we going to do this? Well, the freezing point is somewhere between the two of these. Here's 32 degrees Fahrenheit. What's the total millivolts? Wouldn't the total millivolt reading be the sum of the millivolts between 32 and 75 and the millivolts between 20 and 32? Just let's look those up. Add the magnitudes and be careful with the signs. Take a look at the table. The table is set for 32 Fahrenheit. Let's find 20 degrees Fahrenheit on the table. The reading is negative 0.334 millivolts. The table is telling us that if we had a thermocouple set up like this, with the meter at 32, which is the way the table is designed, and the measuring junction at minus 20, this would be minus 0.334 millivolts. Now let's check the table between 32 and 75 and see what that reading would be. That's 70, 71, 72, 73, 74, 75 is 1.22 millivolts. So the table is telling us this situation. Again, the table assumes that the reference junction is always at the freezing point. This is plus 1.22 millivolts. So the total millivolt reading for our situation has to be the sum of the magnitudes, the sum of the absolute values. Don't add a negative value and a positive value and get a small value. It's got to be bigger than these two. So let's flip one of these around. Let's flip, say, this one around backwards. If we just reverse this meter, right, instead of having the meter at 32 and the measuring junction at 75, what if we just put the meter at 75 and the measuring junction at 32? Then you understand it would be the same magnitude but opposite sign. Now we can add these two together, right? Actually, I don't have to redraw this. I'm doing it anyway. So this would be, the magnitude here is, well, it's minus 1.22 millivolts, and then minus 0.334 millivolts. And our total would be minus 1.55 millivolts to go all the way from here to here, minus 1.55 millivolts. Does that make sense? So the measuring junction is in the ice water salt mixture at minus 20, and the meter is at 75. Calculate the millivolts produced. Well, it would be the sum of the millivolts corresponding to a difference from 75 to 32, plus the millivolts corresponding for a temperature difference from 32 to minus 20. Make sure you add the magnitudes together, and it should be negative because the measuring junction is colder than the meter, minus 1.55 millivolts. Problem number 16, we have this time a copper constant thermocouple, and that's type T. We have to make sure we read the right tables. It's used to check the temperature inside a freezer. A reading of negative 2.13 millivolts is obtained. Seems reasonable. It's negative because the freezer is going to be colder than room temperature, most likely. And our instrument temperature, our meter temperature, is 80 degrees Fahrenheit. Calculate the temperature indicated by the thermocouple. Right, so I've drawn the thermocouple going from right to left, if you will, and we're told that the meter temperature is at 80 degrees Fahrenheit, and it reads negative 2.13 millivolts. What is the temperature here in the freezer? That's a real application. Now we don't really know if 32 is between 80 and our freezer temperature. It probably is, but we don't really know. For all we know, the freezer's not working, and maybe 32 is down here. We won't know until we check out our millivolt reading, but it's likely lies between the freezer temperature and 80 degrees. So how are we going to do this? Well, if we look on the table, we can find the millivolt reading between 32 and 80 Fahrenheit, right? And compare that to this millivolt value. That should give us an indication. So we'll want the type T thermocouple degrees Fahrenheit. At 80 degrees, I already have it circled here, 1.061 millivolts is what you would get with the reference junction at 32 and the measuring junction warmer at 80 is plus 1.061. And that would be what I've drawn here. This would be plus 1.061 millivolts. That's what the table tells us. What we want is the reverse. We want to know, let's switch it around. If the meter was at 80 and the measuring junction at 32, this would read minus 1.061 millivolts. So now I know that the 32, the freezing point, lies between 80 degrees Fahrenheit and the freezer temperature. We have to figure out the freezer temperature. Well, what then is the millivolt reading between 32 and the freezer temperature? Well, it would be 2.13 less 1.061. That's 1.07 millivolts. Now it's going to be negative because the measuring junction is colder than the reference junction. So we can look on our table and find out what temperature corresponds to minus 1.07 millivolts. Minus 11, minus 12, 13, 14, 15, 16, 17, 18, minus 19, and minus 20. Remember the number is 1.07, so it lies midway here between minus 19 and minus 20. Let's try and keep these straight. Let's see, this is minus 19 degrees Fahrenheit, and this is colder. This is minus 20 degrees Fahrenheit. This is negative 1.061 millivolts. This is negative 1.081 millivolts, and we are at negative 1.07 millivolts. So what's that correspond to? This distance, 1 Fahrenheit degree, is equal to 0.020 millivolts. Let's try this distance here. That looks like 0.009 millivolts, right? So we can write 0.009 millivolts times 1 Fahrenheit degree, 4.020 millivolts. That's pretty much a half a degree, isn't it? 0.5 Fahrenheit degrees. We are 0.5 Fahrenheit degrees below 19, so our reading would be minus 19.5 degrees Fahrenheit in the freezer. Right, does that make sense? We're checking the temperature in a freezer. The reading is negative 2.13, which means the measuring junction is colder than the meter. The meter's at 80 degrees Fahrenheit. So what do we start? Well, we can get from the table the millivolts corresponding to a temperature difference of 32 to 80. But the table tells it to us as if the meter was at the freezing point. We have the reverse. We have the meter at 80 degrees. So flip it around, change the sign, minus 1.061. We can subtract that from the total millivolt range, negative 2.13. The magnitude is 1.07. It's going to be negative because it's the measuring junction is colder than the meter. We look that up on the table and we find the bordering values are minus 19 and minus 20, and our value lies midway between them at 19.5 below zero. Right, so problem number 17 is the last one. Using a copper constant 10 thermocouple, that's type T, with a room temperature of 27 Celsius, a reading of minus 0.91 millivolts is obtained. Calculate the indicated temperature. Minus 0.91 millivolts means that the temperature would be colder than room temperature, minus 0.91 millivolts. Room temperature is the meter temperature, that's 27 degrees Celsius. And so what's the temperature here? How many degrees C is that? How are we going to figure that out? what we can do is look on the table and find out the millivolt reading that corresponds to a temperature difference between the freezing point and 27 Celsius. We don't know where the freezing point is, but whatever that gap is, let's find the millivolt reading corresponding to it. Right, so here's 20. 1, 2, 3, 4, 5, 6, 7. That's 27. Be 1.074. If we had a thermocouple set up like this, with the meter at 0 degrees C and the measuring junction at 27, this would be 1.074 millivolts. So that tells us our temperature must be between 0 and 27. What would be the magnitude of the difference then? Let's get that right. I can put it here, or I'll just do it down here. What's the difference between 1.074 and 0.91? 1.074 minus 0.91. That's equal to 0.164 millivolts. So we figured out if the meter is at freezing point, the number of millivolts from there to our temperature is 0.164. Maybe I should make this a little bit longer, just to there. Okay, so what is the temperature that corresponds to a millivolt reading of 0.164? Let's check it out. 556, and here's 195, so it lies between the temperature of 1, 2, 3, 4, between 4 and 5 Celsius. 156 and 195. Let's write those on our diagram. So we have at 4 degrees C, 0.156 millivolts. At 5 degrees C, we have 0.195 millivolts. And we're looking for the temperature at 0.164 millivolts. Right, so for a temperature span of 1 Celsius degree, that's equal to 95 minus 56 is 0.039 millivolts per Celsius degree. And we want to find this span in millivolts. 164 minus 156, that looks like 008. So I can say 0.008 millivolts times 1 Celsius degree per 0.039 millivolts. That's roughly 8 into 40 is about 1/5 is 0.2. So we're saying that we're about 0.2 degrees higher than 4. This looks like it's going to be 4.2 degrees Celsius. So does that make sense? We have a type T thermocouple. Room temperature is 27. There's the meter. The reading is negative 0.91. It's cold. Calculate the indicated temperature. All we can do is look on the table between 0 and 27 and find out what that magnitude is. The table tells it to us as if the meter is at 0. So I write it this way. The meter at 0. 1.074. So what's the difference in the magnitude? The difference is 1.074 minus 0.91 is 0.164. What would that be as a temperature above the freezing point? We can look on the tables between 4 and 5 and interpolate from there. So those are all the thermocouple problems in this unit. Certainly sufficient for you to master calculations like this. Expect at least one thermocouple problem on this test.